What's up everyone, welcome back. I'm not going to do much of an introduction in this video because if you watched the previous video, which you should if you haven't already, you kind of already know what we're going to be doing in this video. We're going to be writing the parser for the lexer that we wrote in the previous video. So let's jump right in. Okay, so in the previous video, we wrote the lexer for the teeny tiny compiler. If you haven't watched the previous video, I highly recommend checking that out because you'll have more context in terms of like what each token is while we go through this video. So we've written the lexer. We have all these collection of tokens that we would have created using our lexer from the previous video. And what we're going to do in this part is we're going to write the parser part of the compiler, right? And so in the blog post, Dr. Henley is actually talking about, okay, you can see here on the left hand side, those are our tokens we talked about in the previous video. We've got this box, the parser, and that's going to spit out an abstract syntax tree, an AST as they call it. Generally, you don't, for this particular tutorial, you don't need to know anything about ASTs. He's just using them to like illustrate generally what would happen if you tokenized and parsed a different grammar, right? So this is the fun part of the compiler, right? We're actually going to start talking about grammars here. You can see above, like where I just scrolled past, he actually parses out an English language, right? An English sentence. And you can see like there's a verb and a determiner and a noun and all these other things, right? So you could construct a grammar effectively for the English language, which, you know, we talk about all the time in English schools. At this point, what he's going to do is he's going to say, okay, we're going to take these tokens, we're going to create ASTs out of them, and to do that we need to have a grammar that explains like the rules of the language. And that's what he's doing right here. Is he's talking about, okay, here's one particular rule of our grammar. You have a statement, print, expression, or string, right? So a statement in our grammar for this particular language means that there will be a print string somewhere, and then followed by that there will be either an expression or a string and then a new line, right? And that's what the pipe symbol means in the grammar, in this particular grammar. We're not actually going to use the grammar. There are certain like tools out there for compilers where you can actually just like give it a grammar and it will construct the parser for you. But in this case, we're actually going to be writing the entirety of the grammar in Python, which was one thing I really liked about this tutorial. So as I said in the previous video, when I wrote my own compiler in college, we used all of the tools, and they were a little bit over my head, right? Because I wasn't a compiler guy, and nobody in that course really was a compiler guy. We weren't professional compiler developers, right? This was actually kind of more useful than the class that I took, because you're really just translating this grammar, these rules right here, and writing them in Python. And so it was like much clearer as to like what is going on when you try to take a grammar and translate it into code to actually have these tokens that we're going to be passing from the lexer and actually parse them out. So right here is the entirety of the grammar for this particular compiler that we're going to be writing for this subset of the basic language, right? And he goes through all this in the blog. I'm not going to go over it now, but he explains like what each of these rules mean. And at this point, he's explaining why we have to split up the math terms like in a certain way. Like there's a reason why your grammar ends up being super complex when you start talking about expressions, and that's because you need to do order of operations effectively at that point. So having done all this setup, you know, we're going to actually start writing the parser, and to do that we're going to set up a little main function here in order to test. And at this point our compiler is actually going to be able to take a file, like a source code file, and parse it out, right? We're going to take that input, pass it to the lexer, and then pass the lexer, which will have the tokens. It'll generate the tokens for us and pass that into the parser. The parser will just, at this point, we'll just take the grammar rules for this language and we'll parse them out into an abstract syntax tree. We won't actually build a tree. You'll see later on. At this point, all we're doing is we're just like parsing out that like, hey, yeah, we did in fact parse out this token. He hasn't written the third part yet, which I wasn't aware of, but when we go through the third part, we'll actually do something with the abstract syntax tree to actually, you know, maintain state of the program and actually execute. In this case, we'll be generating C code out of the basic language using Python, of course. So right here, like I said, all I'm doing is I'm setting up the test file. So our main function will just allow me to pass a file. As we're writing the parser, we'll be able to test it out as we call, teeny-tiny.py on whatever source file that we want to test our compiler out on. And this is the fun part, as I said earlier, right? Like, we did all the work to get the tokens created in the Lexer. The coding was not that complex. It was kind of boring. But now we're actually writing the no kidding, meat of the compiler, where we'll be able to pass the source code, and at least we'll be able to print out like some tokens, basically. So we wrote our main method to allow us to test. As I said, it just takes a file and then it runs it through the Lexer and then the parser. At this point, we're going to actually start implementing the parser. And similar to the previous video where Dr. Henley points out, like, hey, I like to set up my classes and just call pass on all of them. They don't actually have anything implemented, but it's like a skeleton for the class. We did the same thing with the Lexer. We'll do the same thing here with the parser. In this case, we're going to implement some really simple utility methods that this class is going to use. We're going to do check token. It's just going to return check that the token is the kind that we expect it to be. And then we're also going to implement match, which does something similar to that as well. These are just two like very basic utility methods that we're going to be calling throughout as we're writing the rest of the parser. One thing I should have called out here is that match will actually abort, right? We'll call abort the system.exit you can see down there. We'll call that method if the token isn't what we expect. Whereas in the other ones, it's just going to return Boolean, like true or false. Is this what we expect it to be? So there's a little bit of a difference between match and check token. Here's one thing that kind of confused me that I'd like to point out is he doesn't tell you what's going into the constructor for this until like later on. So I kept thinking, like, where is this cur token coming from? Where is this peak token coming from? We actually add more things to the constructor at the end as well. I wish like those would have been defined right off the bat. Like the first thing we implemented maybe was a constructor. That would have given me more context as I was writing the check token, check peak, and match functions. But I mean, they're simple enough where it was like, well, we'll figure it out later, I'm sure. So at this point, we're actually going to start parsing. And one thing he points out here is like we want a program method kind of, and this allows us to do some sort of like pre-processing before we go build the abstract syntax tree. So it doesn't effectively it's like the main loop you could think of as the parser, right? You can see here we're just going to keep creating these statements, parsing these statements, whatever you want to call them, in the self.statement line of code, right? And we're just going to keep doing this until the token is the end of file token, right? That's all the parser is going to do. But so we need it for that main method loop you could kind of think of, but also it allows us to like inject code before we start doing the actual iteration through every token as well. So this is what I was saying before, where I was saying like I really like the fact that we wrote the grammar in Python in this particular case, because we literally are just taking this grammar, the first line of the grammar, which is statement is equal to print, which after that follows an expression or a string and then a new line, right? We're literally just doing that here. We're taking that grammar, translating it into Python for our very first statement, if you will. There's going to be a bunch of other ones that follow just due to the grammar, but this one's a fairly simple one. This was very useful because Python's a very expressive language, so it was very easy to just it's like writing English, right? So we were basically just translating this grammar rule of English into Python code, which is very similar to English as well. It really helped solidify some of the concepts I learned back in college when I was learning about compilers. Here we're just writing the parser for the new line. We'll just keep calling this over and over again, right? Anytime you see NL in the grammar that he outlines above, we'll just call this NL method. So it's a pretty straightforward method. So now that we have our first statement, we can actually test something, and that's all I'm doing here is I'm just creating a hello.tiny file. Where again, this little project, this compiler is called teeny tiny, and so he suffixes his test files with .tiny. So really, we're just going to pass this file into our main method that we created earlier in order to do the testing, and we're going to see if we can actually lex and then parse this test file. And would you look at that? It works. Nice. So we were able to lex, print hello world, and then now we're parsing it here. You can see it's just printing out parsing that it's done. It's printed out that there's a print statement and then a new line following that, which that's all we've implemented up to this point. Eventually we're going to parse strings and all these other things, but at this point we're just testing that the initial parsing functionality that we've created actually does work. So at this point we're basically just going to go down that list of grammars for a statement, and we're just going to start implementing them one by one by one. So we've already got the print one, right? That's a valid statement in our grammar. And the next one we're going to do is this if-then statement as well, right? So for any valid basic syntax that our compiler is going to handle, it has to have an if, a comparison statement, which we'll implement eventually as well, a then string, a new line, and then any number of statements inside that then and if, right? You could think of those as like the brackets for C++. Or C or any other bracket language. In this case we're going to use then and end if, which is more similar to like a bash style of syntax. So yeah, we're just going to go down and implement this and then test it and then implement the next part of the grammar, test that, and so on and so on. So here you can see we're going to support a while loop as well, right? And that the syntax is given, or the grammar is given for that. We'll just implement that down because we've already implemented the if-else statements. Now we're going to here implement the while loops. And now here's a bunch of other grammars that our language is going to support. We've got the label, the goto, the let, and the input. He put those all together as one because they're pretty trivial to implement. You can see them here, right? Just copy that code down. It's pretty easy translation from the grammar into the Python code, as I said before. So now, after implementing a bunch of those subsets of the grammar, we should be able to parse out some more advanced looking language here. In this case, we've got label loop, print, hello world, goto loop, right? You could see this being like kind of an infinite loop here, right? Where we just continually print hello world. Obviously, we haven't implemented the functionality for this yet, right? But we're just proving that we can parse a statement similar to this. And in fact, we see that it does work. So here's some of that pre-processing I was talking about before. In this case, the parser would have actually broken before if we put too many new lines at the beginning of the source code file. We obviously know that that's valid in any programming language, right? So one way to handle that is to do this pre-processing before you actually start parsing the language itself. So this is where things get a little complicated. Like I said earlier in the video, this is like doing the math expressions, and you would think it would be like a relatively straightforward thing. Like he says here, you would just think you'd be able to just do expression, primary, operator, primary, right? And just say like make an expression out of an operator and two primaries on either side of it. But you have to kind of break it up like this and give them weird names like unary and primary and all these things. And that's in order to do order of operations on the math side of things, right? So pretty much we're just making sure that the abstract syntax tree does what we expect in terms of mathematics, and so we have to have all this additional stuff added to our grammar. So the root of our grammar for this particular set of grammar that we're going to write, right, is the comparison operator. So it starts with an expression, and then it's going to have, you know, equals, 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 not equals, etc., right? We haven't defined the expression yet, which is what we were just talking about in the previous clip, but we need to start somewhere, and so we're going to start here at the top kind of the grammar tree, if you will, and write the comparison function. One thing he mentions is that he abstracted out the is comparison operator. It's just a check, right? He pulled that out into a separate method so that it makes the code cleaner. I tried to put this as an inner function of the comparison method itself, but it doesn't work, so definitely pull it out as a class level method when you're implementing this yourself. So we've written our implementation of the comparison grammar, right? And as I said before, we called an expression method here, but we haven't actually implemented it, so we're going to go ahead and implement it right here. It's pretty simple, right? You can see it just expects a term, a plus or a minus, and then another term, right? And we haven't defined term yet, right? But we'll do that next, immediately afterwards. So we're just kind of, like I said, starting at the top of the grammar tree, if you will, and working our way to the bottom. Again, this is kind of funky, right? Because this expression, we have to break these expressions up into like specific types of expressions, right? We can't just say primary operator primary because we need to do order operations. And in this case, right, we're writing a term, which is what we're defining as it's a minus and a plus, or a plus, right? That's a term type of expression, and you'll see below unary is a slash or a star, right? We're giving them these odd names so that we can have order of operations whereby we do the division and multiplication before we do a plus or a minus, for example. So at this point we've implemented our term and our unary. Like I said, those are only just to split up the math operations. And now we're going to write kind of you could think of it as the root of the expression grammar tree, or sorry, the leaf of the expression grammar tree. At this point we're going to write the primary, and that's just a pretty simple one, right? It's either a number or an identifier. It's, like I said, all the way at the leaf of the tree itself. It's like the most basic thing we can define in this grammar. And now we test something that's going to actually look a lot more like a programming language if you're a programmer. Right here at this point we're going to set a variable equal to foo, and that variable is going to be bar times 3 plus 2. Now you'll notice we haven't defined bar anywhere, right? And our compiler won't say anything about that. It'll just let us construct this variable out of thin air without letting it previously anywhere else, which that's fine. We haven't implemented that part yet. We'll get to it, but this is actually something like, okay, now we have expressions, now we can start doing actual computation. And you'll see I'm getting an error, right? This is what I was talking about earlier, where I tried to make this an inner function, and I was able to quickly fix it because I knew exactly. As I was writing, I was making a mental note going, I think this probably isn't going to work, but I'll give it a shot anyway, because it actually needs self inside there, and anyway. So now, after making the fix, you can see that the test passes, and we're actually able to parse out what looks like an actual program, right? He gives us a little extra test to try and parse that as well, and then later he'll point out what I already pointed out, whereby the compiler should also check that bar has been defined previously. In this case, he's saying you shouldn't be able to print an index and go to main. You shouldn't be able to go to something that doesn't exist effectively. And you'll see here that I had a little bug actually, so it didn't totally work. There was a small bug in the code. I'm not going to go into it because it was so insignificant. But so at this point we're going to make the fix to fix the undeclared variables that I was mentioning before, right? He mentions like there's actually a couple things. I'm not that familiar with the basic language, right? But there's actually a couple things you need to maintain. It's not just like which variables have been let before this one, but also like which labels have been defined. In this case, you need to define a label to go to, right? And so you can't go to something that hasn't been labeled previously, right? So we need to maintain those, and we also need to maintain any of the symbols that we let as well. And then we're also going to actually maintain a set of the go-tos as well, so that at the end of the program we can kind of like diff those and make sure that there aren't any go-tos that haven't been gone back to effectively. So yeah, we're just going to create these sets in the constructor, and then we're going to set them at various points throughout the code while we're making, while we're parsing out variables effectively. So now that we have the set, right, we're able to add that to the check token statement, right? So if somebody tries to declare a variable that's already been declared previously, right, we'll throw an error there in that case. So similar to how we use the program method to do some pre-processing, if you remember, we were parsing through all the new lines so that any source code could have new lines at the beginning. We're going to do the same thing here at the end. We're going to do some post-processing after all of the tokens have been parsed. Effectively, what we're going to do is check if a go-to has been called on a label that doesn't exist, right? Another reason why we're maintaining both the go-to set and the labels declared set. So here we're going to check the token. If it's an input token, we're going to mark this label, right? We're going to say that we've seen this as a previous label before. We're going to add this to the set, right? At this point, we're just going to add the symbols that we've seen throughout various parts of the code in order to enforce that, a symbol has to be declared before it's used. And here we're going to do the same thing in primary. We're going to check, see if this symbol's already been used before. If it has, we're going to throw an exception. Or rather, exit the compiler and throw a warning to the user and let them know that. So at this point, we're going to try testing our lexer and our parser together with a more advanced program. This is actually Fibonacci. If you remember from the previous video, he mentions like this is the kind of program we're going to write a compiler for. And so at this point, we're going to do a no-kidding test. Make sure that our lexer works, it's lexing the tokens, it's passing the tokens to the parser, and then we're actually able to detect, or enforce a grammar, if you will, for this basic programming language. And as you can see, everything works. that's everything for this week's episode. Don't forget to like and subscribe, of course. This week's episode was a little bit funner than the previous one. I told you we kind of had to slog through the more tedious coding in order to get to the more exciting stuff in that video. So we took the Lexer stuff, all the case switching and just creating tokens, and we were actually able to enforce a grammar this time, which kind of shows you what makes up a programming language, kind of what it would take to make your own programming language. As I said earlier in the video, there's a bunch of professional tools that do this stuff for you if you're going to go make your own programming language, right? They have all this tooling that they've accumulated over the years, but I think it's actually a better learning experience to write it in Python, which is what we did here. We were able to like more directly translate the grammar that he defined for this basic programming language into code, and you're able to see like what makes this up. I think also the fact that it was like super basic, right? Our programming language doesn't really do much compared to a more advanced programming language like Scala or something like that. But so one thing I noticed is he hasn't uploaded part 3 of this yet. So eventually what we'll do is we'll create an emitter, and I'm going to keep my eyes on his blog. I might even reach out to him on Twitter and let him know I'm doing this series, and maybe crack the whip on him and get him going a little faster. But yeah, so I'm going to keep my eyes open for this one and make sure I get that part 3 eventually when Dr. Henley releases the blog. But for now, that's everything for this week. I'll see you next week.